Okay, so here we go. Here's the final part of the final exam review, part 4. So you need to know the names of your phase changes. Gas directly to solid is called deposition. So you need to know there are 6 types of phase changes. You need to know all those names. Liquid to a gas is boiling, or it is also sometimes called vaporization. Either one of those would be correct. Okay, so we're looking at gases and how they behave under different conditions. In order to decrease the pressure, you would want to increase the volume. Increasing the volume gives the gas particles more room to move, and therefore they're not colliding with the walls of the container as much, which results in a decrease in pressure. Okay, if you decrease the volume, that means that you're forcing those particles closer together, which means they're going to be colliding with the walls of the container more, which is an increase in pressure, but it's also going to be an increase in temperature. Again, because when you increase the temperature, the particles are moving around faster. They're punching against the walls of the balloon, the sides of the balloon harder and more often, which results in more pressure, which pushes the balloon out, causes it to expand. The Gay-Lussac's law shows the relationship between pressure and temperature, and it says that the two are directly proportional, which means if one goes up, the other's going to go up. So if you increase the temperature inside the container, it's going to increase the pressure, which if the piston can move, the pressure is going to force that piston to move up because those particles are moving faster and trying to get farther apart. Okay, what is the name of the process for ions being separated and surrounded by water molecules? That is called solvation. It is the process by which things dissolve. Factors that affect how fast something dissolves include surface area, agitation, and the one that this one is talking about is temperature. A higher temperature allows more collisions. Those collisions are happening faster. Anything that increases the number of collisions between solute and solvent is going to speed up that process of dissolving or solvation. Solubility of gases is a little different from solubility of solids and liquids. Generally speaking, they have the opposite behavior. If you increase the temperature, think about leaving a can of soda out or a bottle of soda out where it's room temperature, it's going to go flat a lot faster than if it was in the refrigerator, because at higher temperatures, gases are less soluble. Okay, so talking about saturation levels, unsaturated means you've got more room to dissolve stuff. Saturated is the maximum amount that you can have, and then supersaturated is under certain conditions you can get a solution to accept more solute, but typically saturated is the most you can have. Forward and reverse reactions proceeding at equal rate, they cancel each other out. That is called the state of equilibrium. Energy is not created or destroyed. It's the law of conservation of energy and the first law of thermodynamics. Things that will affect the rate of reaction, similar to the rate of solvation, but some of it's different. Nature of the reactants will, concentration. Nature of the reactants, because some things are just more reactive. Concentration, if you add more stuff, they're going to bump into each other more, which leads to more reaction. And temperature means you've got more collisions happening at higher energy, so that's going to increase it. So actually all of these will affect the rate. Catalysts are substances that lower the activation energy for a reaction but don't get used up. So the only one of these that's not true is that a catalyst can initiate a reaction. It helps a reaction get going, but the catalyst itself does not initiate the reaction. Increasing the concentration of H2O. So this is about equilibrium and how you shift equilibrium one way or another. Well, in order to increase, since H2O is on the right, we need to have something that's going to shift the equilibrium toward the H2O. That will have it increase. So if we increase the pressure, that's going to actually force it to the left, because that's the side with fewer moles of gas, 6 versus 8. Increasing catalyst doesn't affect concentration, just the rate of the reaction. If you decrease the pressure, that's going to draw the equilibrium toward the side with the higher number of moles of gas, which would be the right-hand side that we want to get to. Increasing the temperature, since heat is on the right, increasing temperature would shift it to the left. A catalyst lowers the activation energy required. Okay, which of the following would cause equilibrium to shift to the right? Pressure. Pressure would have no effect because there's 2 moles of gas on either side. The amount of heat, since heat is on the left, if you increase the amount of heat, that will force the equilibrium to the right. Increasing the concentration of iodic acid would force it to the left on the opposite side. Volume would have no effect, so heat would be the right answer there. Okay, we want to shift this time to the left. Which of the following would do that? Decreasing heat, no, that's going to pull it to the right. Decreasing the volume, this has 4 moles of gas, this has 2 moles of gas. Decreasing volume favors the side with the smaller number, so that's going to go that way. Increasing the pressure also favors the side with the smaller number of moles of gas, so that leaves D. If you decrease the concentration of N2, since that is on the left, that will pull the reaction to the left to make more nitrogen to make up for what you took out, so that gives you D. Okay, talking about acids and bases here. H2SO4, what type of, what species is that in this equation? It's here. You have to look at what is it going to do. Well, it's going to lose one of these hydrogens. It goes from H2 to H1. So it's going to donate a hydrogen ion, which makes it an acid. Key terms here: ionizes partially and produces OH. Okay, produces OH makes it a base. Ionizes partially means it's weak. So put those two together and you get weak base, A. All right, H2O in this equation, what species is H2O? Well, what's going to happen to it? It goes from H2O to H3O. So it gains a hydrogen. It gains a proton. It's a proton acceptor, which makes it a Bronsted-Lowry base. Definition of an Arrhenius acid is a species that produces hydrogen ions. Arrhenius base would be produces hydroxide ions. pH level, okay, tells you about the concentration of the ions. So high pH, so remember the scale goes from 0 to 14 with 7 being neutral, and the lower it gets, the more acidic, the higher it gets, the more basic, and this is neutral. So if you have a high pH, we're going to assume it's higher than 7 toward the base side. So we're talking about something that's a base, and a base is a solution that has a higher concentration of hydroxide ions. So that's going to be answer choice B for base there. All right, so here's some pH values, similar type of question. Which is the most acidic? Well, the most acidic would be the lowest number. Remember the 0 to 14, acid is 0. So the closer to 0, the more acidic. 3.0 is the lowest number we have here, so that's going to be choice C for soda water. Some calculation problems here. These are gas law problems. And the first one is the pressure versus the temperature. And pressure and temperature are directly related. Okay, so they're in a proportion like this. P1 over T1 equals P2 over T2. And our P1 is given as 1.5 atmospheres over T1, which is 25 Celsius. Remember, you always have to convert to Kelvin, add 273 before you put the temperature into these formulas. You get 298 Kelvin for that one. And then we're trying to find P2, that's our unknown. The pressure goes down to 0. Well, 0 plus 273 is 273. And if you do that out, you can cross multiply, and you end up with a result of 1.34 atmospheres. So the next one is pressure and volume. Pressure and volume are inversely proportional. Pressure 1 times volume 1 equals pressure 2 times volume 2. Plug in your numbers. Pressure 1 is 3.05 atmospheres, and volume 1 is 4.3 liters. And that equals the pressure 2, which is 6.5 atmospheres, times the unknown volume 2. Solve for that by dividing both sides by 6.5, and you get a result of 2.0 liters, rounded to two significant figures because there's only two significant figures there in 4.3 liters. More gas law, we've got pressure and temperature, or sorry, volume and temperature, which actually is set up the same way as pressure and temperature. It's a direct relationship. P1 over T1 equals V1 over T1 equals V2 over T2, and then plug in the numbers. You've got 60 milliliters as your V1. Your temperature is 273 Kelvin, 0 plus 273. And then you want to know what volume, V2, it will occupy at 235 Celsius, which if you add 273 is 508 Kelvin. Cross multiply, and you get volume 2 equal to 112 milliliters. And again, some common sense checks on this. The temperature goes up, the volume should go up. Okay, it didn't quite double in temperature and it didn't quite double in volume, so that makes sense. Okay, we have to keep the temperature here below 90, so we're going to try to figure out, we've got pressure and temperature again. P1 over T1 equals P2 over T2. Plug in the numbers we're given. It says 2.33 atmospheres when the temperature is 17 Celsius, which would be 290 Kelvin. 17 plus 273. And we want to know what's the pressure going to be if you pump up the temperature to 90 Celsius, which is 363 Kelvin. Cross multiply, and you get P2 equals 2.92 atmospheres. 0.92. So temperature goes up, the pressure goes up, so that at least makes sense. All right, one more gas law problem here. Actually, two more coming up. This is what's called the combined gas law. It's got pressure, volume, and temperature. So P1 times V1 over T1 is equal to P2, V2, and T2. And we've got a pressure 1 of 1.09 atmospheres and a volume of 32 liters. The temperature given is in Celsius 32, which is 305 Kelvin. That's going to equal the second pressure, which is 0.926 atm, times the second volume, which goes down to 30 liters, over the unknown, which is T2. So you're going to have to do some cross multiplying here, and you end up with T2 equals 243 Kelvin. All right, this is the last gas law problem. It's an ideal gas law. How do you know? Because it's given you grams, which means you're going to need to find moles, and you're only given one set of variables. You're given temperature, volume, and the number of moles. So you're not given two sets. That would tell you it's one of the P1 over V1, P2 over V2. So the first thing we need to do is convert from grams to moles, and we do that by dividing 90.66 grams by 32 grams, which is the molar mass of oxygen, and we get 2.83 moles. Now we can plug that in for N in our equation, and we're going to have P equals nRT over V. That's how we're going to solve for pressure. So P equals 2.83 moles times R, and since we're given, or we're being asked to find the pressure in kPa, we have to look up the value for R that goes with kPa, and that value is 8.314. And the temperature was given to us as negative 35 Celsius, so negative 35 plus 273 is 238 Kelvin. And then we divide that by the volume, which is given as 59.3 liters. So carry out all that math and you end up with a pressure equal to 94.4 kilopascals. So the state that it would be in at 1 atmosphere and 50 degrees Celsius. First of all, you need to remember what the three regions of the graph or diagram are. This over here is the solid, this is liquid, this is gas or vapor. Those mean the same thing. So what would it be at 1 atmosphere, which is this line here, and 50 degrees, which is right here? That puts it right here in this area, which is the solid state. of the phase diagram. What would happen if you had it again at 1 atmosphere and you change the temperature from 200, which is off the chart, down to 150, which would be, put it right about here? Well, actually no phase change occurs because it starts out in the vapor region over here somewhere and it drops down still into the vapor region. If you kept going along that line, eventually it would turn into a liquid, which is condensation. But that's not the question here. What phase change occurs when the pressure goes from 0 at a temperature of 50 degrees? Well, you're starting out at 0, which is the gas state, and it goes up, 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 and it crosses from the gas to the solid. That is called deposition. There's no liquid in between. It goes straight from gas to solid. That's called deposition. And then what would this be at 2 atmospheres and 100 degrees Celsius? Here's 100 degrees. Follow that line until it gets to 2 atmospheres right about here. That's in that region that's liquid. Okay, we need to find the molarity of this solution. So the first thing we need to do, because molarity equals moles per liter, but we're not given moles, we're given grams. So we need to convert moles to grams, or sorry, grams to moles. We do that by dividing the grams given, which is 85.0, by the mass of the compound, which happens to be 85, and that tells us we're going to have exactly 1 mole of compound. Molarity equals 1 mole divided by the number of liters. 750 milliliters. In order to convert milliliters to liters, you move 3 places to the left. 0.75 liters. 1 divided by 0.750 is 1.33 molar. Some equilibrium questions here. So would the concentration of H2O increase, decrease, or stay the same? Well, what happens if we add CH4 is that it's going to shift equilibrium to the right, and H2O is on the left. So you're shifting away from that substance, which means the concentration is going to decrease. Anything on the same side that you're adding to is going to go down because it's going to shift away from that side. All right, we're decreasing the amount of H2 in this second part. Decreasing the amount of H2, which is on the right, is going to pull equilibrium to the right. And since CH4, methane, is on the left and we're going to the right, it is also going to decrease. So decrease for the first 2 answers. Part 3, we're decreasing the pressure. So decreasing the pressure favors the side with the larger number of moles of gas. Okay, the left-hand side has 2, the right-hand side has 4. So we're favoring the right-hand side, which is where the carbon monoxide is, so that's going to increase. If the equilibrium shifts to the right, what happens to the temperature? Well, the temperature is on the right, so the temperature is going to increase because you're going toward the side that has the heat on it, so you're going to make more heat. And if the volume is decreased, that would be the same as increasing the pressure, which favors the side that has the smaller number of moles of gas. So decreasing the volume is the same as increasing the pressure. And we're talking about something that's on the left-hand side, so that's also going to increase. Okay, pH of an HCl solution. This is pretty straightforward. It's a HCl solution, so that tells you that the concentration of the solution is the concentration of hydrogen ions. And to find the pH, I'm just going to take the negative log of that number. Negative log of 0.0564 is 1.25. What's the pH of this solution? The trick here is that this is an OH solution. So I can't find the pH directly, but if you remember that 14 is always pH plus POH, that means that 14 minus POH gives me the pH. So I just kind of have to go around and work this backward. So 14 minus POH. POH is the negative log of the OH, which is this number, OH concentration, same as the concentration of the solution, 0.094. And when I do that out, 14 minus the negative log of that number, I end up with a pH of 13.0. That's the pH. That's it. That's the last part of the final exam review.